So I think we'll get started here if last people get their seats. Oh, that's my seat. So it's a pleasure to have Markus Greiner here from Harvard. So Markus is a leader, a pioneer in the field of quantum simulation of neutral atoms. He, in his PhD, had the first observation of the superfluid to Mott insulator transition. I realized, as I was thinking about what I would say here, that for some of you in the audience, you weren't born when that happened. So like maybe it's like, I don't know. But for many of us, this is like a very important tool, and Markus observed it first. After his PhD, he was actually here for his postdoc in Debbie Jin's group, where he really sort of, with Cindy Riegel and Debbie, observed many of the amazing things that are possible with fermionic quantum gases. And then in 2005, he moved to Harvard as a PI, where he, again, did something extremely innovative, which is sort of pictured here. This is the quantum gas microscope. Markus will tell you more about it, but basically this allows you to really resolve individual atoms in a single site level in standing waves of light. This has been a revolutionary technology. One of my favorite stories about Markus, don't worry, is that when I was a student, I was at the BEC award ceremony, and Markus and Emmanuel Bloch were both getting it for the junior and senior award. And Tillman Esslinger, so the three of them were actually in the lab together when they observed the superfluid to Mott insulator transition. Tillman was running this session, and I couldn't really tell whether this was a little dagger or not, but he said, I remember back when we were in the lab, Markus thinking about developing a microscope and putting it into the experiment in MPQ back in 2000s. And of course, it took several years to do this, but Markus was thinking about this long ago. So Markus has been recognized for many prizes, including a MacArthur Prize in 2011, the APS Rabi Prize in 2013, and other awards. And with that, it's a pleasure to have you here. So take it away.
Yeah, hello. It's really great to be back. I always love to come here, and had the absolute best time here as a postdoc at Gilla, of course. And luckily, I still have a lot of contacts with many of you, and really enjoy coming back. And I think I'll be back often. And does this work? Yeah, thanks a lot, Adam, for the nice introduction also. And so let me update you a little bit of the things that went on recently. Sorry. There are a lot of new things, a lot of things happening in the field of quantum simulation. And so what's really nice is that with ultracold atoms, is it good, the audio? Okay. What's nice is that with ultracold atoms, there is a possibility to build really complex, highly coherent many-body quantum systems that can be controlled in a really pristine fashion, and where we can build really complex models that are extremely difficult or sometimes impossible to compute. And so that's a great opportunity. It all starts with a magneto-optical trap, as you know, if you do cold atoms. So here's an old movie actually I did as during my master thesis in Munich. But you see the atoms, how they are cooled, and then laser cooled and fly apart very slowly because they are cold. Of course, as you all know, in our ultracold atom experiments, we're even much colder with evaporative cooling in the next steps and so on. And then we can build these highly complex many-body quantum systems. And in particular, we can build models, all kind of models, but what we have mostly done is build models that have some relationship to the kind of models that you have in condensed matter physics. Or in other words, you can think of our atoms that move in the periodic potential landscape. Here are our atoms. By the atoms that move in the periodic potential landscape formed of light, like our optical lattice, you can think of them as an analog to electrons moving in the potential landscape of a crystal lattice, right? And then we can realize from first principles kind of fundamental models also simplified models that in and of themselves are hard to compute, hard to understand theoretically. There are many open questions, but we can really build those models and then do quantum simulation to answer those kind of questions. And so this was really it was really fun to kind of start doing these ideas a bit more than 20 years ago of really doing quantum simulation, essentially. And as Adam said, we then added microscopy to the game. And that brings it to the next level, where we can then really take a projective measurement of the whole many-body wave function. And so here, the amazing thing is you can see each dot is exactly one atom, right? And before we take the picture, if this is a Bose-Einstein condensate, right, then before we take the picture, every atom is really everywhere. It's delocalized coherently. And only as the first photons are being scattered, the wave function collapses, and the atoms kind of, well, decide where they should be. And then in the end, we get one projective measurement, one snapshot, essentially, one projection from the many-body wave function. But always keep in mind, if you see these pictures, before we take the picture, the system is in a superposition of all kind of different possibilities that exist, which is an extremely large number in a system like this, of course. And then we take a projective measurement and can get all kinds of information, get high-order correlation functions, and whatnot. Before I dive into the physics, let's just go back a step. If you haven't heard that much yet about atoms in lattices, just how this works. So how do we build these complex many-body systems? Essentially, the atoms are our Lego pieces here. And then how do these atoms move in the lattice? Well, here you can see atoms move in the lattice in real time. But of course, this isn't quantum, right? Because we are watching them, we constantly collapse the wave function, and this would not be quantum. So in reality, we always do the time evolution in the dark, essentially, without watching the atoms. And then in the end, we take one picture. And so if an atom moves into in the lattice, it's doing this via tunneling, right? So it tunnels from lattice side to lattice side. And to illustrate that, let me show you some experiments where we just prepared an initial state of exactly one atom on a side and then let this atom move, right? Like classically, this would do some kind of like diffusive motion, random walk. But in the quantum regime, right, you have to think of this as a wave function. And then as time evolves, the wave function spreads out and tells us the probability to find a particle at some location. And if we take a measurement after this expansion, then we see the atoms appear at these locations. And there are actually very nice related experiments recently in Adam Kaufman's group here that really bring measurements like this to the next level. But just, again, keep in mind, if you see a picture like this, you see an atom here or here, before we take the picture, it's really in a coherent superposition of being here and being here. This just tells us the probability to find the particle. And so if you repeat it a lot, we can then backtrack the amplitudes here, the amplitude of the wave function. How coherent is this? And a nice way to see this is if we tilt the lattice, because then you get coherent Bloch oscillations. So what you expect is the particle at first, again, delocalizes over many sides. But if and only if this is completely coherent, then you would expect the particle to come back to its original lattice side periodically. And so this is like a spatial Bloch oscillation. And if it does, that tells you directly that, yes, you're completely coherent. And so if you try this in the experiment, you see that after a while, the particles perfectly come back to their initial position. Right? And it can only do that because it was in this very coherent superposition. Right? If there was any kind of measurement going on and this system gets knowledge of if it's left or right, it wouldn't know which lattice side to get back to, right? Or if there's any dephasing or so. So this just illustrates you how coherent these ultra-cold atom systems in the lattice are. But of course, well, it wouldn't be much fun to play Lego with one Lego piece. So we do many-body physics. If we have more than one piece, so what comes into play in addition? Well, first of all, there's the quantum statistics, right? It makes a difference now. Are these bosons or fermions? And secondly, the particles interact with each other. For example, if you have two particles on a side, they may repel. And this is an on-site interaction, like a repulsion on a lattice side. Or what I will show you later in the second part of the talk is actually you could even have long range, like dipolar interaction, for example. And so this gives very nice ingredients. And if we put it together, we get even emergent phenomena that are, yeah, even more crazy. Good. So let me tell you about some recent things we did with these quantum simulations. At first, I don't want to talk I don't have time to talk in detail about this, but one recent thing we did is that we added an artificial gauge field. By essentially shaking the lattice in particular ways, we can Floquet engineer a motion of a particle that corresponds to the motion of a charged particle in a magnetic field. But then we can also do this in a strongly correlated regime where the particles also interact with one another. And as you may know, in that regime, you expect a fractional quantum Hall state. And for two particles, we have been able to show exactly that. We have shown how essentially the two particles sit in each other's vortices. And that corresponds to kind of like attaching a flux to a particle. A vortex in a particle wave function here, if this was a charged particle, then this vortex would correspond to a flux line. And the particles can avoid each other by sitting in each other's vortices. And so that corresponds to particles attaching to a flux line. And so we have been able recently to show this two-particle fractional quantum Hall state. And by measuring the correlation functions directly, you can see how the particles sit in each other's vortices. Or what we do recently here also via Floquet engineering, you can engineer more interesting particle behavior. In this case, you can engineer anionic behavior, and we did quantum walks, kind of similar to what I showed you. For a single particle, you can do a quantum walk with two particles that then obeys anionic statistics. And so that's a nice building block also. And currently, we are doing experiments with more than two particles and also in equilibrium to prepare the ground state in a system like this. Yeah, but this was just a quick teaser. So if you're interested, you can look at these papers. What I would mostly like to talk about are two topics today. So one is Nagaoka ferromagnetism, and the second are dipolar quantum solids. So let me start with Nagaoka ferromagnetism. Here's the team. They did amazing work. And we also collaborated in theory with Richard Scaletta, Eugene, Ivan, and Isan on this topic. So the idea is how can we get ferromagnetism? So the funny thing is, if you think about magnetism, the normal magnetism is ferromagnetism, right? That's what we are used to since we have been kids. We have been playing with magnets, right? And they attract each other. And of course, you have elementary magnets. We then learned elementary magnets in your magnet, and they form a ferromagnet. And we are all used to that, right? But wait a minute. If you think about it, this is pretty crazy. What is ferromagnetism? Ferromagnetism means that spins in a material, for example, should all align in the same direction, right? Why would they do that, right? If you have two spins like this, and if you just consider magnetic spin-spin interaction, they want to be anti-aligned, right? They want to look like this. And if you align them in the same direction, if you align them in the same direction, right, this would be energetically unfavorable. So how do you get ferromagnetism, right? Because the ferromagnet would then be a big arrangement of spins that all do the wrong thing, right? Well, this was a big question actually already in the 60s, and the amazing thing is, to answer this, this is a highly non-trivial question. In fact, there is no classical way of understanding why the spins, the electrons in a ferromagnet would actually align like that. You need a lot of quantum mechanics for that. You need Pauli exclusion. You need strong interaction between particles. And it's not the magnetic interaction. In fact, the magnetic interaction is usually negligible. That's why this is possible in the first place, right? You need so you need Pauli exclusion, fermions. You need strong Coulomb interaction, and certainly strongly correlated, strongly interacting electron gas, oftentimes even strongly correlated electron gas. And so this is why in condensed matter, in actual material science, it's often highly non-trivial to understand what makes a good magnet. Okay. Now, we have been in the 60s already. Hubbard wrote down his famous Hubbard model. And so he was asking, what's the simplest model that we can write down for electrons in a material, right? And it turns out a major motivation for him to write this down, and you can look at his original paper, like I think he mentions ferromagnetism at least 30 times in his paper. A major motivation was to see if this model already gives you ferromagnetism, if this explains a magnet, right? And okay, what is this model like? So the simplest possible model is you just have fermions in two spin states, right? Like electrons in your conduction band, kind of. And then they can tunnel between lattice sites, just like the particles I showed you earlier. And then there is interaction, like Coulomb interaction, or let's make it a pure on-site interaction, just two particles on the same side. There is no magnetic interaction here, and this is because they had, of course, already realized that the magnetic interaction, the direct magnetic coupling between electrons is weak. Right? So he wrote this down and calculated and so on, and it turns out, so what does this predict? It turns out the dominant effect here on the spins in this system is superexchange, is spin exchange. The basic idea is that this kind of model actually, at half filling, favors antiferromagnetic spin alignment, it turns out. Because if two spins are in the opposite direction, then they can hop on top of each other and exchange. But if they're in the same spin direction, they cannot even virtually go to the neighboring side. They're completely stuck because Pauli exclusion forbids you to go there. Right? So they want to be anti-aligned and create an antiferromagnetic state. And so, in fact, this Hubbard model predicts an antiferromagnetic ground state. So it did not explain ferromagnetism. And in fact, so this model became very famous then a bit later because it is believed to be a minimal model that may even capture high temperature superconductivity, just this model. Maybe adding one more term or so, some diagonal tunneling or so. And this is actually a major field in quantum simulation right now, to build this model and simulate it and see if it can actually create things like, strange metal phases, pseudo-gap phase, and then also D-wave superconducting phases. So that's a big push. I won't be, and this is also kind of like an important goal in our Fermi-Hubbard quantum simulation here, but I won't be talking about anything antiferromagnetic today. I just want to mention that yes, then with cold atoms we can build exactly this model, and then we have very nicely seen exactly this antiferromagnetic ground state of the half-filled Hubbard model. Good. So Hubbard model alone didn't really help, but by the way, but in the a few years later, Nagaoka actually found a way how the Hubbard model can lead to ferromagnetism after all. And this is called Nagaoka Ferromagnetism, and what I will be talking about experimentally today. The idea is that, or what Nagaoka's theorem claims, is that if you have a single dopant, like a half-filled Hubbard model, but then you have a single dopant that moves through the lattice, and if the interaction, the on-state interaction, is infinite, then the ground state is a long-range ferromagnet. That's the famous claim by Nagaoka. So how can that be? The basic idea here is the following. If you have a dopant in your half-filled lattice, so the two colors are the two spin states, and you can have different spin patterns, right? If you have a dopant here, and that dopant moves through the lattice, it does make a difference for the dopant what the spin pattern is. If, in particular, if the dopant moves through here, it actually changes the spin arrangement. It turns out it actually works exactly like a puzzle like this. So each time the dopant, essentially the dopant and the next lattice side, they exchange essentially, and so that moves the spin pattern around, and the final spin pattern is different, which means that the spin pattern encodes the path that the dopant took, right? And that means that different paths can't interfere because you have the which way information now. So the dopant going this way and dopant going this way, those two processes cannot interfere because from the spin pattern you can read the path it took. But if it can't interfere, that means it cannot delocalize. It cannot minimize its kinetic energy by delocalizing. And what Nagaoka realized is, well, we can get, how about if you have a ferromagnetic spin background? If all the spins point in the same direction, now my dopant can move without giving away the which path information, and hence it can delocalize coherently, and hence it can lower its kinetic energy by delocalizing. And and so then his claim was that adding a dopant can turn the whole system ferromagnetic. Of course, this is a little extreme case here. You need infinite U, right? You actually may need very infinite if you just talk about a single dopant here. But this has been studied a lot, but despite a lot of studies, there are actually many open questions on how this generalizes. But let's first discuss, so is this how ferromagnets work? No, it's not. This is not how your normal ferromagnet works. A normal ferromagnet also needs a model like this Hubbard model, but then you need to add additional bands, right? Additional orbitals, and then you still need Pauli exclusion, and then the different orbitals, you then have Coulomb repulsion between different orbitals. And again, it gets very complicated, but you can, if you have higher bands in your Hubbard model, then you can understand how a ferromagnet forms, or how your ferromagnet that you know from your iron or so forms, right? So this is different, but it's different in an interesting way, because in the former case I just described, where you have this multi-band Hubbard model and so on, the motion of particles usually tends to work against the magnetism. Here we have magnetism that just occurs if you have motion, so kind of kinetic magnetism, this is often called, right? So yeah, it's not your usual magnetism, but it's very interesting magnetism because it's caused by the motion of the dopants. There was an experimental realization in 2020 with the 2x2 quantum dot plaquette, so on a plaquette, and actually Anna-Marie Viaret had predicted some nice things on Nagaoka here on a plaquette. There you can see that very nicely. But of course, the plaquette is quite simple, so we want to push it to larger systems now. And also what I will mention later is, just as of this year, there are actually 3 realizations in twisted bilayer materials, like TMD materials, where they see ferromagnetism and believe that this is the same kind of kinetic magnetism. So there's a very nice connection now between actual condensed matter physics and TMD materials and these quantum simulations. Okay, so For infinite U, a single dopant can turn everything around, essentially. But is this actually, but of course you would expect this is a somewhat fragile effect, and theoretically it's not really understood particularly well how this plays out. One thing that's clear is that for any kind of square lattice system, as I was showing here, this ferromagnetism is quite suppressed because if you have any finite U, if the interaction is only finite, then it always favors antiferromagnetism, and that's what you have to fight. And so because of that, we did these experiments in a triangular lattice. So triangular lattice means we change the geometry in a way so that we get spin frustration, right? If you have a triangle, the first spin is up, the second one is down. What should the third one do? It's frustrated. It doesn't know what to do, right? And this, of course, helps if you want to get ferromagnetism. Then this quenches. Oops, sorry, I turned already. This then reduces your antiferromagnetism. So how can we create triangular lattices? There are different ways to do it. You could directly have 3 lattice beams interfere, for example, but we do it a bit differently. We have interfering lattices here in the x and y direction. If the two don't interfere, you get a separable lattice. If they do interfere, you get a non-separable lattice with the potential landscape as shown here. And what we can then do is we can lower the lattice depth in one direction, and that way we create a triangular, a tunable, like we can continuously tune from square to triangular geometry, just by turning on this diagonal tunneling across one of the directions. And if you do this, we can then image the spin patterns that we get at half filling. And you see here for the square lattice, we get our antiferromagnet, as we had it before. But then as you turn on this diagonal tunneling, the geometry changes here from an antiferromagnetic pattern into one where you have a triangular symmetry or hexagonal symmetry here. And you also see overall, of course, antiferromagnetism is being suppressed here. That's what we are interested in the context of Nagaoka magnetism. We can Fourier transform these spin-spin correlation functions, and then you can nicely see how the spin-spin correlation, so this is the spin structure factor here, derived by the Fourier transform of these correlation functions that we can then nicely measure directly in the quantum simulation. When we did this here at half filling, and then we start doping the system with either holes or doublons, then we can study how this magnetism changes. And so for a square lattice, famously, you would expect this to be completely symmetric between hole and particle doping, and that's exactly what we found. But if you now go to the triangular geometry, then you see it actually becomes very asymmetric here. And to our surprise, we found that if you dope a lot, if you have 50% more doublons here, then we actually saw that the nearest neighbor correlator turns ferromagnetic. And the question is, so is this kinetic magnetism? Yeah, it seems like this is certainly going in the right direction. And so here again, you see that up here, all the spin-spin correlations turn ferromagnetic. But, well, it is kinetic magnetism, but it's very far away from this idea of Nagaoka, where he says one added particle turns the system ferromagnetic, right? But the nice thing is with the microscopy, we can now go ahead and just see what a single particle does. Meaning we can do simulations with a few particles, and then we can identify, we can take a snapshot and see where the doublon ended up and investigate the magnetic environment around that particle, like a 3-point correlation functions. And so we can directly see what effect a single dopant has compared to not conditioning that measurement on the position of that dopant. And so if you do this, again, so we say, so if we find a dopant on a lattice site here, if you find a doublon on a lattice site, what are the nearest neighbor spin correlations then doing around that dopant? And we found here for moderate interaction, the nearest neighbors here around that hole are strongly ferromagnetically correlated. Is this already Nagaoka magnetism? Well, the interaction is quite strong. You would actually expect Nagaoka to happen at higher interaction strengths. And in fact, yes, one has to be a little careful, because if you then look at correlations further away, they are still zero. So this only has a very local effect. And if you reduce the interaction further here, then we actually see we even get kind of an oscillating behavior even in this kind of metallic phase. So it turns out this is actually more like a Friedel oscillation. And so this isn't really Nagaoka. For Nagaoka, we expect this to have a longer range kind of effect. But what if we increase the interaction now? And so we were able to increase the interaction without increasing the temperature much. And then if you measure the nearest neighbor correlators further away from that doublon, we see a marked difference here. So in this case, over these 20, 30 lattice sites around the doublon, we see a significantly higher probability to find this ferromagnetic correlation. And so this essentially is the this is the Nagaoka bubble. If you have a doublon here, right, it wants to delocalize to minimize energy, but it can only delocalize if its environment is fairly ferromagnetic. And so essentially, this doublon trying to delocalize turns that environment around it ferromagnetic. And if we take these snapshots and we condition the measurement on having found a doublon here, right, then we see this Nagaoka bubble, essentially. Right? Yeah, and so this shows that effect directly, and is really realizing this idea of Nagaoka that a single dopant is doing something. And here we can kind of see how that plays out. As I said, the nice thing is it actually links to some recent condensed matter research with twisted bilayer materials, where you see similar ferromagnetic, or they claim that that they also have kinetic magnetism. It's a bit unclear if it's Nagaoka, but the interaction is very strong. So this may indeed be a Nagaoka magnetism in the real material. But also, it's very difficult to compute things. Like, for example, the regime in which we do the measurement here, the theory people can only do at about twice the temperature that we have. At the current temperatures we have, you can only do a system that is significantly smaller than our experimental system. And so this is really getting into a regime where it's really hard to compute things, even with the most sophisticated numerics methods. And but we can do these quantum simulation. And so it's a nice example for how we can play with the system. We kind of stumbled across this, actually. This wasn't our original plan. We were surprised when we doped the triangular lattice that suddenly the correlated turned ferromagnetic, and then we zoomed in more into this Nagaoka kind of regime. Good. And yeah, and so there are lots of exciting things to do. I mean, on this Nagaoka also, there could be pairing and things like that. But as I said, we are also pushing towards now really getting to colder temperatures, also in the square lattice or square lattice with T prime, to really address questions like this pseudo gap, strange metal, D-wave superconductivity, and so on. There are lots of activities going on worldwide, and actually, I should mention, in Adam and Cindy are collaborating also on a new experiment there that really should bring this even to the next level with even much longer lifetimes that should be able to get even much colder and so on. So this is a very exciting time for these kind of these Fermi-Hubbard systems are just amazing because they're so hard to compute. Because of the sign problem, you really have problems to compute these many-body quantum states on a computer, and it is believed that the sign problem may be real, meaning it reflects a real complexity that you. I mean, it could be that tomorrow someone figures out a way how to do it, but people have tried very hard, and it seems to be genuinely hard to compute these things. And then when you talk about dynamics, like in strange metal or so, then it's even much more hard. But of course, these things can also be done experimentally. Good. So this is Nagaoka magnetism. In the second part of my talk, let me tell you about another nice new tool that we can now use, namely have long-range interaction, have dipolar interaction, because that, of course, opens a lot of new possibilities if we can realize models that are beyond just this pure on-site interaction. So as I showed you, right, normally atoms tunnel on the lattice side, they feel each other with on-site interaction, right? But wouldn't it be nice if you can also have long-range interaction in the system, right? One motivation is, of course, if you want to understand something like what electrons do or so in some shielded potentials, there's still some long-range contribution, right? Or even anisotropic, right? Attractive in one direction, repulsive in another. There's a whole zoo of things that is an amazing ingredient. But how could this be done, right? So what's nice is that these long range, it naturally promotes all kinds of spatial structures, right? You could create supersolids or things like that. It creates frustration, right? And promotes entanglement, essentially. But how to do it? And actually, who really showed a beautiful way on how to do it was Dabijin, Junyi, and Kankweni here. With making ultracold molecules, right? So the ultimate gold standard to do experiments like this will be molecules, no question. You can have, with molecules, you can have very strong electric dipole moment, and then you can build models where you have strong dipole-dipole interaction between the particles. There's been amazing progress over the last few years with like but the problem is still to get it cold, to get like how can we initialize it at very low entropy? How can we have exactly one molecule per lattice site and do everything at high fidelity? And there's amazing progress, but there's still a bit of a path ahead. But recent things like microwave shielding and DC shielding, some of this pioneered here, makes me very optimistic that ultimately these are the systems you want to use. Ultimately, there are, as you know, Rydberg atoms, right? They make nice longer range interaction. They work best, of course, in this kind of Ising regime where you can do quantum gates, quantum computation, and so on. But you can also use them in some kind of XY model kind of range. But if you talk about itinerant physics, so people have tried about Rydberg dressing, but it seems tricky. There's always a lot of loss involved in that, but we'll see. Of course, there are other things like cavities. The problem there is also how do I get into a strongly correlated regime, right? Where you really have where a single photon, a single atom has strong effects on your many-body state. And then, of course, in condensed matter, right? A lot of those systems have naturally long range. Oftentimes you can't turn it off, right? But they also become more and more programmable, of course. So that's like the twisted bilayer that I was just mentioning, of course, these long range also play a big role. What I will be talking about here is a different approach and just saying, well, I know magnetic interaction is weak, but can we make it strong enough somehow, the direct interaction between magnetic particles to do dipolar physics, right? So that's the big question here. You can use atoms that have a strong magnetic dipole moment. And so Ben Lev, Tilman Fau, he pioneered chromium, Ben Lev dysprosium, and Francesca erbium, where you have magnets that have atoms that have a fairly strong magnetic moment by themselves already, and that boosts those effects, of course. And there's beautiful recent work, for example, seeing a superfluid where a Bose-Einstein condensate breaks up into these puddles that but you still have coherence across those puddles, and so it's a super solid, essentially, where you have simultaneous some spatial order emerge, but also coherence between them. But the question is, of course, what I'm interested from a quantum simulation point of view is, can we have strongly correlated quantum states, the kind of like Fermi-Hubbard, Bose-Hubbard kind of, because that's where you really have the really hard to understand physics and like a lot of entanglement present and things like that. And the problem is with the magnetic interaction, it's quite weak. If you have a normal optical lattice, you put rubidium in, you have 0.1 Hertz interaction between neighboring sites. Right? If you use erbium, you have a bit more. You have like 4 Hertz interaction, but it's still quite low. What Francesca Ferromagnetism showed already is that, well, this scales with 1 to the third, right? So you can, if you have the lattice spacing, you use green light instead of infrared light, you can actually boost it quite a bit to by an order of magnitude to about 30 Hertz interaction strength between neighboring lattice sites. And what Francesca Ferromagnetism showed is already she saw a measurable, a detectable shift in the superfluid mode transition. So there is it has some effect on the strongly correlated physics, even though it's still a quite low number. But the question is, can we make this the dominant effect? Can we arrange everything that this dipole interaction is the dominant term in the Hamiltonian? And so that's what I'm gonna talk about in this talk, and what we built an experiment for to try that out in collaboration with Francesca, who taught us how to work with erbium, and we're collaborating. We show her a bit on how to do microscopy. That's a fun collaboration. And here's the current team, but of course I should also mention the first generation team who actually built that amazing apparatus and got that to work. And one of the nice things they got to work is actually that we can have a high repetition rate. And I can tell you, my other 2 experimental teams are so envy now, because it makes a huge difference if a measurement takes, I don't know, a week or a day, or if it takes a day or 20 minutes or 10 minutes, right? So you can actually, in erbium, you can optically cool it pretty much very close to BEC, and then within a total of 600 milliseconds from start to finish, we can make a BEC from scratch. So now we finally can do experiments where the preparation of the cold atoms takes less time than we then use to do the many-body physics. So okay, and then I said we want strong interaction, so green lattice. Let's make green lattices with half the usual lattice spacing. But then we also want microscopy. And that's, of course, a bit challenging, because we now have even half the spacing between the atoms. So how can we detect them reliably? And there's some additional complications with the atomic physics there. We may need magic wavelengths and so on. So we decided to go a totally different path, namely to make an accordion lattice. So we use we have a very high numerical aperture objective inside the vacuum chamber. We're not only using that to image, to scatter photons, but also here you can see a picture how we put it in. So we also use it to create a lattice potential that we can zoom in and out. So first we have a green standing wave like this, and then we superimpose a lattice made out of blue light that comes through the objective that exactly matches this. And then we can, change the laser beams and increase that lattice spacing. At least conceptually, it's very, very nice and simple. And we designed a way that also makes that very doable in real life. Here you can see just a little movie where you can see so this is, the objective is behind here, and in the Fourier plane you can see how these beams move in and out with like galvo mirror-driven periscopes, and then we have a special built a special optical setup that creates pairs of beams that move against each other and make this accordion lattice. And once we do that, of course, we have a large spacing between the atoms, 5 micron spacing. So now we can very comfortably and easily image the atoms within only a few microseconds. We essentially do flash photography. We shine a lot of resonant light onto the atoms, totally saturate the transition. It's actually similar to what Junier is doing in strontium here. And then, but here we can then resolve all the individual atoms very reliably with 99.8% fidelity or so, within only 5 or 10 microseconds of imaging time. So that's, that is quite useful. Good. So now that we have this lattice, what can we do? So we have the tunneling here. We have the on-site interaction. And now we also have a dipole-dipole interaction. So we get an additional term in the Hamiltonian interaction energy, not just with two particles on the same side, but also if you have them on neighboring sides or even further away, they interact according to dipole interaction. And we can, of course, orient these dipoles and things like that. And as I said, this energy scale is about 30 hertz. The on-site interaction, we have about 1 kilohertz. So this is hardcore bosons now, for now, where this is just a constraint that limits it to 1 atom per side. And then the tunneling, well, we need to reduce that to about 5 hertz tunneling. So it's ridiculously low energy scales. And the big question was, is that possible? But the idea is essentially that we adiabatically reduce the tunneling. So here's a superfluid Mott diagram. This is the chemical potential and the tunneling. And if we come from large tunneling here at half filling, then we follow between the n equals 0 and n equals 1 Mott insulator at half filling into this superfluid. But we can now zoom in here, and at very low tunnelings, we have these. We have all kind of interesting quantum phases emerge here now that are caused by these dipolar interaction. And how we prepare it is we start with the superfluid, and then we move into this regime where we expect the quantum solids, and we do a quantum phase transition from the superfluid into these the states that you expect if you have dipolar interaction. This is the theory predicting it. There's a lot of very nice work, for example, by Barbara Kappa-Grosses and so on this topic, but also many others. Because, of course, the idea of having molecules was on the horizon a long time, so there's a lot of theory work. In 2022, we saw the first correlation. So yes, we saw if we align the spins perpendicular to the plane, we saw some anti-correlation. The particles try to avoid each other on nearest neighbors, or if you point it this way, they like to point in the same direction. But of course, this is far from a ground state, right? It's just some weak correlation. So the big question was, can we go to the can we go close to the ground state of the system? And just to show you how hard this is, this order needs to be much less than 30 hertz, right? Because 30 hertz is our dipole, so this order needs to be much less than that. But that means in a lattice depth of 200 kilohertz lattice depth, you need to have less than 30 hertz disorder. So you need less than 0.01% disorder. So you have to be very careful that your laser beams don't scatter at the windows, all kind of things like that to get into this regime. And then the temperature, right? At 5 hertz tunneling, you need a few hundred picokelvin temperatures, essentially. Is that possible? Well, and the idea is that as you reduce tunneling adiabatically, you actually adiabatically get to these low temperatures. So let's try it out. If we, like after a lot of optimization, if we have the atoms perpendicular to the plane here, what happens? What do you expect, right? What kind of shape do you expect at half filling if you have repulsive interaction? Right? Well, they don't want to be next to each other, right? Half filling, so they should form like a checkerboard. Right? And in fact, that's what we see in the, that's what we see in these pictures. Oftentimes we get pictures that look quite nice, like a checkerboard. You see this is empty, and there's an atom, atom empty, atom empty. It's not always this perfect. So on average, we get correlation plots like this, and this would then be the corresponding structure factor. But we can nicely get into this regime where the dipole interaction is really the dominant term. And in a similar fashion, if the dipoles are now in the plane, but they attract, they repel, so what's the ground state now? Well, of course, you would expect some stripes, right? Like this. And in fact, yeah, that's a picture. That's the kind of pictures we can take. And here the fidelity is a bit higher, actually, because this attractive interaction is twice as big than the repulsive interaction. And so we can get this striped ordered state. Let me point out that, of course, ultimately, this state is in the kind of, so this checkerboard and stripe sounds very classical. But yes, for zero tunneling, these are classical states, kind of, right? But the question is, how do they change as we turn on quantum mechanics. And we actually come from the other side. We start with a superfluid. So we come from a very quantum mechanical system and then do a phase transition into these states with stripes and checkerboard. And so that means these are interesting phase transitions. They are oftentimes first order. They're believed to be first order in some cases. And there is a lot of interesting questions to ask, because at first you can imagine you have like macroscopic quantum fluctuations of stripes being here or here, and so there's a lot of interesting quantum mechanics happening on the way. In fact, we have started to study the first order phase transition here and found some evidence for microemulsion. We find like at random places there is more like checkerboard behavior, more like stripe behavior, and this seems to be random and not pinned to any disorder and so on. So, but we just started to study this, so this is very preliminary. One thing, what do you expect if you point the spins diagonally, right? So we tried that, and yeah, sure enough, we saw some nice diagonal stripes. Is that what you expect? It actually turns out we then did numerics, and no, numerics didn't predict that. And we did it again and again and checked the numerics, and then we realized, wait a minute. If the stripes are aligned like this is actually not the ground state. The ground state is actually, so we tried to vary the time then, and depending on how quickly we ramp, we can see different stripe spacings. In the Fourier transform, this is nicely visible, these two peaks moving closer and closer together, and ultimately, if you're adiabatic, you get the phase separation, because the particles prefer to all clump together into one oval kind of shape. That is the ground state, your phase separation, if the dipoles are completely in the plane. And so it was fun to see this and to see these metastable states, actually. It turns out if you tilt it a bit out of the plane, then the actual ground state does become a diagonal stripe state. And in fact, there's a whole zoo of different states here. And we started exploring this. Let me not go too much into detail, except for saying that, so what's kind of cool is seeing any diagonal stripes already shows you that we are not just next neighbor, and we are not just sensitive to next neighbor interaction, because diagonal you only have next nearest neighbor, and then but this even goes beyond, and so we can only make this agree with theory if we go beyond nearest neighbor, next nearest neighbor, and if we even go beyond that, then we can make this agree with theory. So this is really dipolar interaction, anisotropic dipolar interaction that we are showing here. And just for fun, a little movie, what happens if we rotate the spins around, the dipoles around. Yeah, so we were quite excited that we can actually do this ground state physics. A whole other topic, I don't really have time to talk about this, and it's also very preliminary, is you can also do spin models. I just want to mention it briefly because Anna Maria Ray has done some really nice proposals here, and so this is why I wanted to show you the progress on this. The basic idea is, so what I showed you so far had no spin, just motion of particles and then repulsion or attraction of those particles. Here's now opposite. Here I'm considering a fixed arrangement of particles, and then the spins talk to each other. And if that is the case, right, for example, in metrology, an interesting question is, can we do squeezing in such a system? And can we use interaction for squeezing? Because if you have many such spins, right, they can be represented on a big Bloch sphere. And if you create squeezing, then you can trade the noise in one quadrature with noise in the other quadrature and get better clocks or better measurements via squeezing. And usually this is done with an all-to-all interaction, one axis twisting, kind of like in a cavity, like what June is doing in his strontium clock. But Anna Maria Ray figured out, wait a minute, I can actually also do this with long-range-ish interaction. Like you don't need all-to-all interaction. And you only need moderately long range, depending on the dimensionality, actually. You need different kind of fall off of interaction. Let me skip all the details other than saying that the prediction was that with dipolar interaction in 2D, you could actually get nice squeezing. And so we started to try this. We have a clock transition that is very magnetic field insensitive. and then we do the squeezing, and we need to read out, of course, with very high fidelity. Actually, by now, the fidelity is much higher. It's 99.8 as of last week. And so we are trying to see the spin. This data is, the first thing is we just prepare a spin on this big Bloch vector. Depending on the angle, we can see how it now precesses, because the squeezing is caused by some shearing motion. So we can map out this shearing motion here. So that works exactly as expected. And then we can try to measure the squeezing. And so here, this is kind of like how wide your ellipse is as a function of angle. So it gets wider a lot. It doesn't get very much narrower yet. But we are still limited heavily here by some classical noise, because as you know, it's already hard to do a quantum limited measurement, but now you have now we want to see 10 to 20 dB squeezing, so we have to measure even much more precisely, and so we are learning a lot. But we believe that the states we are creating, everything points to them already having 10 to 20 dB. Squeezing, but we can not show this yet. So this is, some work in progress, but I just wanted to show, because Ray had some really nice ideas that are now explored in not just these dipolar atoms, but also with Rydberg, for example, and with molecules that could also work beautifully. Good, so I showed you Fermi-Hubbard quantum simulation and what's all possible there. In particular, I showed you this Nagaoka ferromagnetism, and finally we can do physics with dipoles. And so this, that leads me to thanking the team. It's an amazing team that's very productive, and so it's a very exciting time on this experiment. I would also like to thank all the funding agencies, and thank you very much for your attention.
Thank you for the great talk. So we have time for questions.
Mm-hmm. The diagonal stripes? It's actually this can be understood quite nicely, because so this is the interaction plot here, and for example, for this angle as shown in this drawing here, the interaction has a very nice simple form, right? So here there is no interaction with nearest neighbor, or like all along the x or the y-axis, there's no interaction. And so the problem is, if this is closer to in-plane, then you have a lot of attractive interaction here, x and y, and that's why atoms clump together, because overall you have attraction. But if you tilt it out of the plane here, then you have no interaction for nearest neighbor. You only have beyond nearest neighbor interaction, okay? And then this beyond nearest neighbor is repulsive in this direction and attractive in this direction, and that then leads to those stripes, right? So it wants to have the atoms form diagonal stripes, because it attracts them one way and repels them the other way. But it's actually remarkable that we can see that, because this is yet a factor of 3 or so less interaction. So the interaction strength here is less than 10 hertz, right? But yet it can give rise to, it can give rise to diagonal stripes. Does that make sense? Is that answering your question? No?
Maybe we can move on.
Okay, let's talk later.
When you show the phase diagram,
Mm-hmm. What feature? Like an insulator, kind of not superfluid anymore, and solid as in it spontaneously breaks symmetry, right? yeah, so translationally, and so here, for example, if you have the checkerboard, right, it could be on the even or the odd sides, or if you have the stripes, it could be on the even or odd. If you have, for some of these other stripes, there are even more possible positions, right? So it's a different. I'm sorry. Right. So these patterns can be differently. They are not, and in fact, we do see them randomly, right? So it's yeah. So there's a spontaneous symmetry breaking, and that's why I would call it a solid. Right. Of course, there is still the lattice, right? But the different ways, different patterns you can spontaneously form. Right? Does it make sense? And then as you do the phase transition, the complexity arises from, like, as you start forming these patterns, you're very much in a superposition at first of different, right, of different possibilities, and then you kind of settle into one. Right, like odd and even stripes, like initially as those stripes start to form, there's a lot of quantum fluctuation on the, like, that's very strongly correlated things happening at that transition, right?
I'm just wondering, would fermions fall underneath the same category as the Nagaoka Ferromagnetism?
So
Fermion being the vortex field.
uh-huh.